Dr. Y. Sarada, Professor, Department of Mathematics, Anna University. Her area of specialization is applied probability and stochastic modeling. She has about 25 research publications in national and international journals. She has guided students for research projects. She has delivered lectures in her area of specialization in many institutions.
Welcome to the UGC lecture series on queuing and reliability. In the last lecture, we got started with the derivation on the generalized Poisson queuing model. Let us continue with that. The Kendall notation for this generalized Poisson queuing model is Mn1 Gd infinity infinity. So, where we said the rates are dependent on the state of the system, be it the arrival rate or the departure rate. The probabilities we saw for each type of event is as given here, P of 0 arrivals and P of 0 departures in T to T plus H. Each one of these, the probabilities means the rates are proportional to the length of the interval. So, we went on to write the probabilities of all the mutually exclusive events. So, we arrived at the differential difference equation, namely dPnt to dt or Pn dash t is minus of lambda n plus mu n into Pnt plus lambda n minus 1 Pn minus 1 of t plus mu n minus 1, it should be mu n plus 1 into Pn plus 1 of t, n equal to 1, 2, 3 and so on. Well, the equation what we saw till now is valid for those values of n starting from 1, 2, 3 and so on, because we are representing the count, that is the number of customers. So, 1, 2, 3 is fine, but there is a possibility that there could be no customer in the system at time t maybe. So, that is the case when we have n equal to 0. So, we need to write a separate equation for n equal to 0. That is what we have here. P naught of t plus h minus P naught of t is equal to minus lambda naught h plus order of h into P naught of t plus P1 of t into mu 1 h plus order of h. So, this we have, namely the procedure is the same. The whole interval what we are interested is of length t plus h. This interval t plus h is divided into two parts. One is 0 to t, the other one is t to t plus h. So, the previous interval is of the length t, the next interval is of the length h units of time. So, once again as before, we need to look into at time t plus h the count is 0. So, that is possible. Initially at time t equal to 0 we have no event. So, t equal to 0 we have 0, and at time t if the count is 0, then it should continue to be in 0 until time t plus h. How is this possible? We are considering two types of events, one is arrival, the other one is departure. Arrival increases the count, whereas the departure decreases the count. So, at the outset we need to have no arrival, no departure in the time interval of length h units of time. So, we have P naught of t into 1 minus of lambda here, but then when there is no customer in the system, it is absurd to talk about no departure. So, you talk about the departure of a customer only when there is at least one customer in the system. So, that is the reason why we do not have a minus mu naught in this part, first expression. This actually is P naught of t plus h is equal to P naught of t into 1 minus lambda naught h plus order of h. probability of no arrival in the knowledge that no customer is there in the system or 0 customers at time t in the system is given by 1 minus lambda naught h plus O of h. So, from that 1 into p naught of t, that has been taken here onto the left, and hence we have this expression out here. So, this first term on the right hand side calls for no arrival in the time interval of h units of time. The second term corresponds to at time t there is one customer, fine. Then in the interval t to t plus h there should be one departure, so that the count goes to 0 at time t plus h, and also there should not be any arrival during this interval of time. But when you multiply this mu 1 h plus O of h with probability of no arrival, once again you have h square terms, they are negligible, and hence they are absorbed into this O of h. That is why we have this second term written as P1 of t into mu 1 h plus O of h. As before, we take the limit h tending to 0 on both sides of this first equation, and then divide both sides by h. Then we are into, on the left hand side, p naught dash of t, that is what is written here, or it is dp naught t by dt, which is equal to minus lambda naught p naught of t plus mu 1 times p1 of t. So, this is valid when n equal to 0. So, in the essence, now we have two differential difference equations, one equation for the case when n equal to 0 written independently, the other equation is valid for the values of n starting from 1, 2, 3 and so on. So, the next step is how to obtain the p and t from these differential difference equations. Once you talk about a differential equation, we need to assume or have a initial condition, because there would be a constant involved in the integration after you solve this differential equation, and that constant has to be obtained. So, for that purpose we need the initial condition, and that is what we have next, namely p naught of 0 is equal to 1. So, this is true in the sense, in the definition of the Poisson process, which is basically a counting process, we have that at time t equal to 0 there is no event in the system, that is there is no customer in the system. In other words, we have n equal to 0. So, then what happens about the probability of such an event? But that is a shear event, because any counting process will have that at time t equal to 0, when you start the experiment you do not have any event in the system. So, that is a shear event or a certain event. So, the probability of such a certain event is 1. So, hence we have p naught of 0 to be equal to 1 here, and p n of 0 for any other value of n other than 0 is 0, because one's total probability should add up to 1 at time t equal to 0. So, not only that, you do have, this is a shear event. So, there cannot be any other possibility, that is at time t equal to 0 you cannot have finite number of customers or even one customer to be present in the system. So, these comprise the initial conditions, and then we are into obtaining the steady state probability p n of finding n customers in the system. So, that is obtained as following here: mathematically, limit t tending to infinity p n of t is equal to p n. So, in whatever differential difference equation we have dpnt to dt in terms of lambda n plus 1, p n plus 1, p n minus 1 and so on. So, that is a differential difference equation. Our aim is to solve that equation and obtain p and t. Now, after getting p and t, is it possible to get p n? The answer is yes, because you allow t tending to infinity in this asymptotically, we mean, or it is the long run steady state, or it is said that the system reaches an equilibrium state. So, these are the other synonyms used for the steady state probabilities. So, we are going to do all this to the set of two differential equations, difference equations we had obtained earlier. So, because Pn is a constant steady state probability, but dependent on n, we have as limit t tending to infinity what happens in the steady state. So, we consider dPn t to dt to be equal to 0. Since Pn's are constants, we have the derivative of that to be 0. So, in other words, the notation wise we have limit t tending to infinity Pn dash t is 0. This is true whether n equal to 0 or 1 or 2 and so on. So, now we are into these equations. We have the so called balance equations. So, in the previous step where we have this differential difference equations, suppose we allow t tending to infinity of all this, right. For example, consider this equation P naught dash of t equal to minus lambda naught P naught t plus mu 1 P 1 t. Now, take the limit t tending to infinity on both sides. Then what happens? The left hand side is 0, because we said for the derivative as t goes to infinity, we have the limit P n t is P n, which is constant. So, the derivative will be 0. So, left hand side here in the case when n equal to 0 will be 0, right. In the case when n equal to 0, t tending to infinity on the left hand side of this equation, it will be 0. Right hand side we are into getting minus lambda naught P naught plus mu 1 P 1. So, what happens to the general case equation P n dash t? Here we allow again t tending to infinity on both sides of this equation. We have left hand side to be 0, right hand side we have minus of lambda n plus mu n into P n, P n t becomes P n, and similarly lambda n minus 1 into P n minus 1, and then here it is mu n plus 1 P n plus 1. So, in the case when n equal to 1, 2, 3 and so on. So, we do have these balance equations once you allow the limit t tending to infinity to the generalized system of differential difference equations, which is valid for all values of n equal to 0, 1, 2, 3 and so on. So, now we are ending up with these balance equations, namely minus of lambda n plus mu n into P n plus lambda n minus 1 P n minus 1 plus mu n minus 1 P n plus 1 equal to 0. After removing the 0, you take this quantity to the left hand side. So, it comes out as plus lambda n plus mu n into P n equal to lambda n minus 1 P n minus 1 plus mu n plus 1 P n plus 1. At this stage, I would like to share with you that the balance equations, the name is justified in the following fashion, namely you have something like you are talking about the arrivals and the departures into the system. So, the rate of inflow is equal to the rate of outflow. When will the state of the system enter the state n? So, that is possible when the left hand side denotes that already it is in state n, then there should not be any type of event happening. So, that calls for the rate being lambda n plus mu n. So, P n already denotes that probability that there are n customers in the system in the steady state. Similarly, right hand side, the two terms indicate that the state n is entered with when the state is already n minus 1, then probability P n minus 1 multiplied with the rate lambda n minus 1, which calls for an arrival which increases the count to n. Similarly, here mu n plus 1 indicates the rate that the state is already in n plus 1. So, one departure takes it to the state n. So, that is why we have the expected rate of inflow is equal to the expected rate of outflow. So, hence the name balance equations. Next, we see that from these equations you solve recursively, we get the probability P n equal to lambda naught, lambda 1 and so on lambda n minus 1 divided by mu 1 into mu 2 and so on into mu n into P naught and n equal to 1, 2, 3 and so on. So, if you see here the rates lambdas in the numerator, they start with 0, and in the denominator the departure rates, they start with 1, n equal to 1. So, that is because the departure rate we discuss only when there is at least one customer in the system. So, at this stage let us take a short break. Welcome back after the break. So, we were looking into the balance equations of this generalized Poisson queuing model. The equations were minus of lambda n plus mu n into p n plus lambda n minus 1 into p n minus 1 plus mu n plus 1 into p n plus 1 equal to 0. So, we said the expected rate of inflow is equal to the expected rate of outflow. So, we had these balance equations. So, the next step is to derive this p n to be equal to lambda naught lambda 1 into lambda n minus 1 divided by mu 1 mu 2 and so on mu n into p naught. We said that the departure rates are valid only even if there is at least one customer in the system. So, mu starts with mu 1 mu 2 and so on, whereas lambdas start with rate of arrival. So, even if there is no customer in the system, an arrival can take place. So, we will next see how to get this expression for p n from this balance equations. So, we start with this. Suppose we have n equal to 1. So, because these balance equations are valid for n equal to 1 and so on. So, consider n equal to 1. Then we have lambda 1 plus mu 1 into p 1. This is equal to lambda naught p naught plus mu 2 into p 2. So, what this is now? We have mu 2 p 2, this is equal to lambda 1 plus mu 1 into p 1 minus lambda naught p naught. We do not know what the expression for p naught is, but we do know what the expression for p 1. So, presently we will see how to derive that expression for p n in terms of lambda naught lambda 1 and mu 1 mu 2 and so on. So, we have these two equations n equal to 0 where lambda 1 p naught is equal to mu 1 into p 1. So, we write this, so this will imply that p 1 is equal to lambda 1 by mu 1 into p naught. So, we are going to use this expression for p 1 in this other expression and get it recursively. So, we will presently consider the second equation, put n equal to 1, then we have lambda 1 plus mu 1 into p 1. This is equal to lambda naught p naught plus mu 2 into p 2. Fine. Now, p 2 is written as lambda 1 plus mu 1 into p 1 minus lambda naught p naught divided by mu 2. So, this now further be written as lambda 1 plus mu 1 by mu 2 into p 1 minus lambda naught by mu 2 into p naught. We use this expression for p 1 as lambda 1 by mu 1 into p naught. So, we further have lambda 1 plus mu 1 by mu 2 into lambda 1 by mu 1 into p naught minus lambda naught p naught by mu 2. So, this further gives us p 2 is equal to lambda 1 by mu 2 plus mu 1, the whole thing again rewritten into lambda 1 times p naught minus lambda naught P naught. Here the expression should be lambda naught by mu 1. The first term always should start with lambda naught. So, I have here this lambda naught P naught into mu 1 by mu 1 is already there because coming from the P1. So, this gets cancelled. I have a lambda naught P naught and this term will get cancelled with lambda naught P naught by mu 2. So, this further giving us P2 is nothing but lambda naught into lambda 1 by mu 1 into mu 2 times P naught. So, we have P2 being written as finally this is equal to lambda naught lambda 1 by mu 1 mu 2 into P naught. So, in this way next step would be to take n equal to 2 and then proceed further. That will give us, because of the presence of mu n plus 1 into P n plus 1 there, we will get P3 in terms of again P naught. Initially we will have P3 written in terms of P2 P1, plug in the expressions we got for P1 and P2 here and get everything in terms of lambda naught lambda 1 lambda 2 mu 1 mu 2 mu 3 into P naught. So, we can now generalize this expression fine and get the expression we need here. That is how we get P n equal to lambda naught lambda 1 into lambda n minus 1 divided by mu 1 mu 2 and so on mu n into P naught comma n equal to 1 2 3 and so on. Now, the whole thing rests on what this P naught is. So, P naught still remains unknown. So, next to find P naught we make use of the fact that sum of total probabilities is equal to 1, that is sigma n equal to 0 to infinity P n is equal to 1. So, this further gives us that P naught is 1 by 1 plus lambda naught by mu 1 plus lambda naught lambda 1 by mu 1 mu 2 and so on to infinity. 6 types of models on queuing theory, particularly the Markovian queuing models. So, to start with we will be doing the single server model with the infinite capacity, namely in the Kendall's notation we have MM1 GD infinity infinity. So, as the notation goes, the first label indicates that of Markovian arrivals, the second label indicates the Markovian departures, number of servers is again 1, queuing discipline is general and there is no restriction on the capacity of the system nor the source. So, the difference between the generalized Poisson queuing model notation and this one, you see that there is no state dependency. Earlier we said this is Mn Mn1, now this is MM1. So, now we are not going to have the dependency on the number of customers present in the system. Dependency here is about the rate of arrival and the rate of departure. So, let us get on to the assumptions of this model. We have the arrival and the departure rates to be the Poisson processes. The rates are lambda and mu respectively. Mean inter-arrival and the service times are 1 by lambda and 1 by mu. Why? Because we have the underlying counting process to be Poisson process, be it that of arrivals or that associated with departures. So, the inter-arrival times in both the cases is exponential. So, the respective means will be 1 by the parameter and hence for the arrivals it is 1 by lambda and for the departures it is 1 by mu. Next we have the assumptions on the probabilities of arrivals and no arrivals, more than one arrival, more than one departure or no departure, all in h units of time, because the basis is going to be the same as we discussed in the generalized Poisson queuing model, namely you will be dealing with the interval t plus h, but then we will be dividing that interval into 0 to t, t to t plus h. So, the probabilities we discuss are going to be mainly in the length of interval h units of time. So, we have the following assumptions again. So, P of 0 arrival in h units of time is equal to 1 minus lambda h plus order of h. P of 0 departures in h units of time is equal to 1 minus mu h plus order of h. 1 arrival is lambda h plus O of h, and 1 departure in h units of time is mu h plus order of h. And probability that more than 2 arrivals happening in h units of time is O of h. Same is the case in the case of departures, where P of greater than 2 or equal to 2 departures in h units of time is O of h. With these assumptions, we are going to start with the generalized Poisson queuing model probability expressions, plug in these expressions for lambda n minus 1 and so on, similarly mu 1, mu 2 and so on, and try to get what the expression is for the steady state probability of finding n customers in the system. So, we go back to the balance equations here and the Pn and P naught which we saw few minutes earlier. So, in the present model we take lambda n to be equal to lambda, mu n to be equal to mu, n equal to 0, 1, 2, 3 and so on, whereas for mu n should be strictly from 1 onwards. Suppose I define rho equal to lambda by mu, then P naught is 1 minus rho. How we get this? We have here P naught is 1 divided by 1 plus lambda naught by mu 1 plus lambda naught lambda 1 by mu 1 mu 2 and so on to infinity. So, what is this lambda naught by mu 1? That is lambda by mu. Fine. Similarly, the third term will have lambda naught lambda 1. So, each lambda I is always written as lambda in this case. Similarly, each mu I is written as mu. So, from the third term here, lambda naught into lambda 1 becomes lambda square and divided by mu 1 mu 2, that will become mu square. So, essentially we have lambda square by mu square, which in turn becomes lambda by mu the whole square and so on. So, in this fashion, if I substitute lambda by mu to be rho, then I am having in the denominator the series 1 plus rho square and so on to infinity. But what is this sum? We can sum up this series. This is the familiar geometric series. What is the sum of that? 1 by 1 minus rho. When I put 1 by 1 minus rho in the denominator, that 1 by 1 minus rho goes to the numerator, hence I have P naught is 1 minus rho, and that is what has been written for you here. P naught is 1 minus rho. Now, plug in this expression in Pn. What is Pn? So, Pn is again lambda naught, lambda 1, lambda 2 and so on, lambda n minus 1. As before I said, all the lambdas be put as lambda and all the mu's be put as mu, then I am into how many such lambdas and mu's are there here? We have lambdas running from 0 to n minus 1. Totally n terms are there in the numerator as well as the denominator. Numerator has 0 to n minus 1 lambdas and denominator has mu's running from 1 to n. So, the count is the same, equal to n in both numerator and the denominator. So, all these are products. So, we have finally lambda power n by mu power n, which is nothing but lambda by mu the whole power n, which is again rho power n into P naught. What is P naught? We just now saw it is 1 minus rho. Hence, we have P n equal to rho power n into 1 minus rho, provided rho is less than 1. But why do we have this condition? We know that for a geometric series, if the series has to converge, then we should have rho to be less than 1. Here, this also justifies with the theory or practical application, namely in the queuing theory you have, what is this rho? Rho is lambda by mu, but lambda by mu is less than 1, that is the required condition, which in other terms means that lambda is less than mu. But what is lambda? What is mu? Lambda is the arrival rate and mu is the service rate or the departure rate. So, for the queue not to blow up, we need strictly that the arrival rate should be less than the service rate. Only then the queue will not blow out. So, we have rho less than 1, which is quite justified for this model. So, we do have in this case the condition that rho is less than 1, which is the condition required for the steady state, namely in particularly the queue not to blow up in the system. So, in this fashion, after deriving the steady state probability, the next step would be that of obtaining the performance measures. So, let us stop here. As usual, like before concluding, what have we done in this lecture? We have seen the derivation of the steady state probability of finding n customers in the system, and together with the condition which is necessary for the system to reach a steady state. So, that is rho less than 1. In other words, the arrival rate is less than the service rate. The students can consider taking down the following problems, whether they have understood the concepts or not. So, the first problem reads out as this: university buses arrive at the student center to take students to their classes according to a Poisson process with an average rate of 5 buses per hour. Chris just missed the last bus. What is the probability that he waits more than 20 minutes before boarding a bus? The next problem says that cars arrive at a gas station according to a Poisson process at an average rate of 12 cars per hour. The station has only one attendant. If the attendant decides to take a 2-minute coffee break when there are no cars at the station, what is the probability that one or more cars will be waiting when he comes back from the break, given that any car that arrives when he is on coffee break waits for him to get back? Thank you.